The second speaker for this session is Irene Tamborra from Niels Bohr Institute, 15 meters from me right now. And Irene will give a talk with the title Supernova Lessons from the Weakly Interacting Universe. So Irene, you can start.
Thank you. So hi everyone, and thanks Eduardo and Andrea for organizing such a nice workshop. So I'm going after the, I thank Gerg also for setting the stage. So now I'm going to build a little bit on the general overview of Georg and focus mostly on supernova and the standard and non-standard weakly interacting particles that we can find in supernova. And since we have a talk in the next few days by Francesca Calore that will cover axions in this context, then I'm going to focus for what concerns non-standard physics, mostly on the non-standard scenarios that are linked to the neutrino channel. So in my talk, I will first introduce supernova, and then I will focus on neutrinos and the physics of neutrinos in supernova and the diffuse supernova neutrino background, the detection chances for these particles, and then we will move on to non-standard particles before to conclude. So supernovae originate from the death of stars that are at least 8 times heavier than our sun. And we usually have an onion structure that forms with the heavier elements that starts to gradually forming at the core of the star. When iron is formed, then the gravitational pressure basically leads to the collapse of the star. And during the explosion of the supernova, we have a huge emission of neutrinos. Basically, almost all the binding energy that is released under the form of neutrinos. And we can either, we usually form then a compact object, and this could be a neutron star, which then you can see would be like a really tiny a star with respect to its progenitor star, or if the explosion is unsuccessful, then we can go directly into the formation of a black hole. And in both these scenarios, we can expect that weakly interacting particles play a very important role. So as I mentioned, during the emission during the explosion of the supernova, the 99% of the energy goes into neutrinos. So we expect a neutrino burst that should carry about 10 to the 58 neutrinos. And given these numbers, you can already gauge as basically most of the supernova physics is then led by weak interactions through neutrinos. So even the explosion mechanism, we think today that is probably also led by neutrinos, in the sense that the shock wave forms. Here you see a section in the core of the star, and basically the shock wave starts in the iron core as it loses all its energy by dissociating iron nuclei. And the neutrinos then provide the new energy to revive the shock wave. And this is what we call the delayed neutrino-driven explosion mechanism. So when we think about effects that are non-standard, that could be connected to neutrinos, we can also think about scenarios that can affect this shock revival and therefore don't lead to a successful explosion, as we will see also in the following of the talk. Now, as Georg also mentioned, we have up to now observed only one of these supernovae in neutrinos. This was the supernova 1997A that exploded relatively close to us in the larger Magellanic Cloud. And we only saw a bunch of neutrino events, but this was the first probe of the stellar collapse. And despite the very sparse statistics, it has been essential to establish and to have basically some indications about the energetics, but also to place a lot of bounds on standard physics. In fact, most of the bounds that we have from supernovae concerning the non-standard interactions are still based on this supernova here. Now, when we think about neutrinos emitted from supernova, then we can produce two classes of neutrinos, either neutrinos with energies around 10 to 15 MeVs, that in the grand unified neutrino spectrum, which also was shown in the previous talk, would fall here in this region. And so we will see here neutrinos from the supernova burst as well as from the diffuse supernova neutrino background. Or we can expect non-thermal neutrino production that instead would occur from the particle accelerated at the shock, while we have interactions of the shock with the CSM medium. So here then we would produce particles with energies of a few tens of TeVs. And we could, in principle, consider non-standard scenarios in both energy ranges if we want. But in the high energy regime, then we produce not so many of these neutrinos. And so given the statistics, we don't have, compared to 1 million of neutrino events, which we could see instead for the thermally produced neutrinos, of course, we have less chances to test non-standard physics through higher energies neutrinos. So in the following, then we will focus mostly on this region here. So when we first consider the neutrinos emitted from the burst of the supernova, and then we will go to the diffuse supernova neutrino background, we expect to see either pre-supernova neutrinos and then neutrinos emitted from the burst, that whose signal we expect to last for about 10 to 20 seconds, and they will be emitted at the same time as gravitational waves, we expect, and then only afterwards we will see photons through the light curve and possibly also the shock breakout. Okay. So when we think about the neutrino signal, if we can divide it in 3 different phases, and you can see that the energies as well as the luminosities are changing as a function of time, but more or less they are around 10 or 15 MeVs. And as for the luminosities, the hierarchy among the neutrinos of different flavors changes also as a function of time. Here, when you see nu x, this means nu mu or nu tau, because we don't have the possibility to distinguish with the, okay, we have some possibilities, but zero order, we assume that both of them are the same. So we have within the first 50 milliseconds, the electron-neutrino luminosity is huge with respect to the one of the other flavors. And then we have the accretion phase, where the luminosities of the electron flavors starts to become more similar to each other. And then soon after the explosion, we have the cooling phase, where the neutrino signals become all similar to each other as the proton-neutron star that just formed starts to cool down. So this is like a standard scenario without considering the fact that the neutrinos can also change their flavor. And in principle, we can consider different, in these 3 different windows, we can consider the different effects. For example, this part of the signal would be independent on the supernova mass as well as the equation of state. And therefore, we expect, assuming that we know what standard neutrinos are doing with the flavor mixing, we expect probably to see, according to the mass ordering, a peak in the electron-neutrino signal, but not in the non-electron neutrino one. And so in principle, if this peak is then not observed, the neutronization burst is not observed, and we know exactly what happens for flavor oscillations in the standard context, then this signal could be used to place some constraints on non-standard kinds of interactions. While in this, during the accretion phase, most of the physics is basically the one that precedes the explosion. And so if we imagine that we know very well what is happening concerning standard scenarios, then we will see afterwards that we can consider various non-standard or new physics scenarios that then can, for example, halt or delay or modify the explosion. And then afterwards, in the cooling phase, we can consider non-standard physics that would lead to channels of extra channels through which the cooling of the star can occur, and this can also help to put some constraints. So this is just to give like a brief overview of the standard versus what we expect in a case that would be non-standard. So if, however, like a big caveat in this game is that we need to know what to expect for the neutrino signal. And in order to do that, we need to understand and to know how neutrinos can eventually change their flavor. And in this context, then we can expect that the neutrinos interact with ordinary matter, and this would lead to the well-known MSW effect, through which we have an enhancement of the conversion of neutrino flavors through forward scattering of neutrinos on electrons. But when the density of neutrinos is extremely high, as it happens in the case of supernovae or mergers, as we mentioned before, then we cannot forget about the coherent forward scattering of neutrinos onto each other. So this is a nonlinear effect because we needed to take into account the feedback of the neutrino field onto itself. And what matters is also the angle between the moment of the colliding neutrinos. So then this becomes kind of an intricate riddle to solve. And in order to tackle this issue, we solve equations of this kind. So usually when we think of hydrodynamical simulations, neutrino transport is not including the mixing of neutrinos. But if we had to include it, then we have a 7-dimensional problem because we have a time, 3 coordinates due to momentum, and then 3 coordinates for space. And the formalism that is used is the one of the density matrix, according to which on the diagonal elements of the density matrix, we have the occupation numbers of neutrinos of different flavors. And then on the off-diagonal elements, we have basically terms that are linked to the probability of neutrinos changing their flavors. And so here then we have a derivative with respect to time. This term here takes into account the advection of neutrinos through, for example, the star. And then we have another term due to external forces, for example, GR, which for simplicity we can forget, although it can also play a role. And then on this other side of the equations, instead, we have a commutator where in the Hamiltonian we include the vacuum term that leads to flavor mixing in vacuum, and then the coherent forward scattering of neutrinos on electrons and on themselves. And then all other collision terms are included in this term, in this last term here. So this is a stiff problem which involves quantities that are changing on very different time scales. And this is why it's kind of challenging to solve it. And so one of the issues is that, of course, as I mentioned, in order to predict and to place robust constraints on many scenarios that involve new physics, we needed to be aware of what the standard scenarios or what the standard physics is doing. And so the current understanding is that we should expect already flavor mixing to occur very deep inside in the core of the source. And this is this orange surface is where neutrinos roughly started to free stream out of the core of the star. And here, this yellow circle is where the shock wave is sitting. So if neutrino, the active flavors are mixing already in this region, we can eventually affect up to some degree also the physics of the explosion. And then we expect, again, collective effects to occur in this green area. And then there will be MSW effects instead occurring at larger radii. So the signal that eventually we can observe at Earth would be affected by all these scenarios. Now, in order to understand then whether these can affect the physics of the supernova and eventually the explosion or not, the approach that has been used very often in the literature is to rely on the linear stability analysis, according to which we don't solve the equation of motions with the density matrix that I showed you before, but we solve the linearized version of these equations. And then this would allow to establish whether there are conditions for flavor instabilities to occur in the core of the star without predicting which is the actual amount of flavor conversions that we have. And so if we play this game, this is an example from one of the simulations of Thomas group, we can see that indeed there are conditions for flavor mixing to occur that seem to be unstable. But the question then to be answered is that whether we expect a large amount of flavor mixing or not. And so this is, as I mentioned, we cannot solve the equations in the full format, but we have started to understand and to try to see whether indeed we should, what we should expect. And what we have found is that indeed there are all the predictions that we can obtain with the linear stability analysis can tell us what are the regions where we should expect flavor mixing to occur, but they are not indicative of the amount of flavor mixing that is taking place. And so in principle, we could have some regions where we can predict that there are flavor instabilities to arise, but the amount of flavor mixing that in the end we obtain is actually very small. And so it has no impact on the physics of the source. However, there are other effects which have been not considered for long times, like, for example, collisions or the advection of neutrinos that can dynamically affect the way flavor mixing takes place. And so in the end, further work is necessarily needed in this context, but we are basically developing a better understanding of how the all flavor physics is basically taking place in the core of the star. So what are then the detection prospects of neutrinos after they leave the star for a supernova burst? And here you see an ensemble of neutrino detectors that are specifically sensitive to supernova. And the ones that are in parentheses are under planning or construction. So at the moment we have several of them. Most of them are sensitive to electron antineutrinos, but some, like for example, Dune, that is currently under construction, will be sensitive to electron neutrinos. And again, this is also very useful if we think of non-standard scenarios that can, for example, affect or be interesting only for specific flavors and not others. So it becomes interesting to be able to discern the different flavors independently. And in addition to dedicated neutrino telescopes, we can also use dark matter, direct detection dark matter experiments to do neutrino astrophysics. And indeed, those detectors, like for example, the xenon detectors or dark side and so on, they employ the coherent elastic scattering of neutrinos on nuclei, which is a process which is flavor independent. And so in this case, then we would basically gain complementarity with respect to dedicated neutrino detectors, since in this case, we would detect the overall neutrino signal in all 6 flavors, while with dedicated neutrino detectors, we would see single different flavors. In addition to direct detection dark matter experiments, we also recently proposed the Resenova detector to be built at the Gran Sasso laboratories, which would be instead based on lead, archaeological lead, and would work basically with the same principle. Okay, so then this is all like the standard stuff related to weak interactions that we have in the context of one supernova burst. But of course, we can also think of detecting the neutrino signal coming from all supernova exploding somewhere in the universe. As Georg already mentioned, we expect about 2 supernovae per century, more or less, in our galaxy, but we expect 1 supernova exploding every second somewhere in the universe. So in this, this is one of the figures that was shown in the most recent paper from the Super Kamiokande collaboration, where they reported up-to-date limits on the diffuse supernova neutrino background. And here you can see those gray lines are the theoretical predictions, and the dots are really falling onto the lines here. So some of the most optimistic models that have been predicted are currently already excluded by the data, and we are soon reaching the threshold for detecting this signal, which will be a steady and guaranteed signal. And of course, this again can also be affected, as we will see later in the talk, by scenarios that are not all involving standard physics. So another aspect to keeping under consideration is that in the plots that I showed you before, we have limits from Super Kamiokande on the anti-electron neutrinos. And however, it's also important to place constraints on the non-electron flavors, because this can help us to disentangle a largest amount of information from the diffuse supernova neutrino background. And here in these plots, you see us both the xenon and the lead-based detectors will be actually excellent in helping us to improve the sensitivity to the non-electron flavors. So in this case, of course, given the statistics that we achieve with these detectors, we won't be able to put to measure the DSMB in the non-electron flavors, but still we would be able to put stranger and upper bounds on the non-electron components. And Anna Suliga afterwards is going to give you more details on this. So one thing to keep in mind, however, is that when we think of learning about neutrino physics as well as non-standard physics through the diffuse supernova neutrino background, we have to fold this with all the uncertainties that are affecting the signal. And in this figure from one paper led by Daniel Kresse, you can see the various uncertainties that are affecting the DSMB. And so most of these are related to astrophysics, and indeed the largest one that we have is the effect basically that we have from the star formation history. And on this part of the plot, you can see instead the effects due to, for example, neutrino mixing, or to the shape or the energy, to the shape of the neutrino spectrum, and also to the average energy of the neutrinos. So if we assume of using then the DSMB as a probe to learn about physics, that weak interactions that could be standard or non-standard, we need to make sure either to look for signatures that could be distinguished besides the uncertainties that we have on the astrophysical uncertainties that we have on the signal, or still these have to be very specific signatures, like for example in energy, signatures in energy, so modulations of the signal and so on, that could be easily discriminated by other astrophysical uncertainties that are still present at the moment on the signal. So now this is all what I wanted to tell you for the standard part. Now let's move on examples of non-standard interactions. And here you see like just a summary of various new physics scenarios, and where supernova neutrinos are placed in an energy landscape with respect to various probes, both from astrophysical sources as well as terrestrial sources that could probe new physics. And so in the context of supernovae, the mechanism that the concepts that we want to use to constrain physics that is non-standard is mostly, for example, if we use neutrinos as observables, then we could impact the signal of the neutrinos either in its duration or in changes in the emission properties that are different from the standard ones. Or at the same time, we can also affect the physics of supernovae themselves. And the scenario that has been mostly considered in the literature, Georg already showed this plot, concerns energy loss arguments, through which basically we assume that we have new particles that will take away part of the energy from the burst. And therefore, for example, we can shorten the duration of the neutrino signal with respect to what is currently expected. So typically the late time signal of neutrinos would be one of the observables for new physics in this context. Now, some of the things that we can learn that are new physics that could be linked to the neutrino signal concerns interactions of neutrinos that are non-standard. And here I show you two examples. The first one is related to secret interactions of neutrinos. So here we are talking about interactions of neutrinos among each other that could be mediated by a new mediator that could be a scalar or a vector. And in principle, if we assume that those interactions occur after the neutrinos leave the supernova, then these neutrinos could undergo those secret interactions with the neutrinos that they meet on their way, coming from the cosmic neutrino background. If this happens, since the cosmic neutrino background, the neutrinos have an energy that is much smaller than the one of the standard supernova neutrinos, then we don't scatter all the supernova neutrinos to small energies. And so instead of expecting then a third signal that would again be peaked around 10 or 15 MeVs, as we already mentioned, we would push the signal to so small energies that in some extreme cases could be undetectable. And indeed, recently we revisited this argument and placed a constraint in the mass and the mediator and the coupling of the new mediator in this region here, which was revisiting a larger region here, this light blue, that was placed through kind of similar but more approximated arguments by Kolbe and Turner by using the neutrinos from the supernova 1987A. At the same time, however, those kind of non-standard interactions could also occur in the core of the star. And if this happens, then we can affect basically the energy deposition into the core of the star. And we have mentioned that we need enough energy that is deposited by neutrinos to revive the shock wave. So we can consider some extreme scenarios under which the neutrinos are interacting so strongly that we basically lead to not enough energy being deposited. And if we use this argument, then we would have this excluded red region in this part here. Now, other kinds of non-standard interactions could be, for example, non-standard interactions due to coherent scattering of neutrinos or nuclei. And in this case, again, we can expect such a kind of interactions in the core of the star. And this would then delay the decoupling of neutrinos from the core of the star. And those are those bounds here in gray. But also we can then expect those kind of non-standard interactions to occur into the detectors themselves. So before I introduced the xenon or resonova detectors, and if we play this game, then this would mean that we would strongly affect the recoil spectrum that we expect to see from supernova neutrinos in the detectors. And so by factoring in all the uncertainties that we have on the oscillation physics, on the supernova uncertainties and so on, still we should be able to constraints or to put some bounds on those kind of non-standard interactions. And those are these regions here that are just projected sensitivity bounds. So of course, while in the case of those neutrino-neutrino interactions, we can already place some bounds even based on the observations of neutrinos from the supernova 1987A. In the case of non-standard coherent neutrino nucleus scattering, of course, we needed to see a supernova in these xenon or lead-based detectors before to be able to place some constraints, but still it's something that can be done. Now, another interesting candidate, which is non-standard, that could be linked and could have an effect in the context of supernova, are sterile neutrinos. So as you maybe know, we really don't have a scale in the context of sterile neutrinos. We can expect a very large range in terms of masses and also in mixing angles. And this picture here is just an example where you can see a lot of bounds that have been placed by various experiments and cosmological as well as astrophysical probes. But it's just to give you an idea of the freedom in terms of mass and mixing that we can expect. Now, in the following, I want to focus on two possible scenarios that are interesting for supernova. And then, of course, we can merge all the situations in between. So one is the one of Kiwi mass sterile neutrinos, and those are well-known dark matter candidates at the moment. And if we assume that we can produce these particles in the context of supernova through flavor mixing, then we expect to convert very deep in the core of the source the active flavors into sterile, and possibly then they undergo into other resonances that bring back active flavors. So these kind of extra ingredients were proposed in the early days to explain or were just invoked to hide the supernova explosions, exactly because we have neutrinos with the very high energy here that are then transformed into steriles. And so this becomes a very natural way to transfer very energetic particles from the core of the star in the outer regions. Now, however, when we consider these kind of conversions between the active and the sterile flavors, of course, we modify the lepton asymmetries that we have in the supernova core. So here you see a simple expression that tells you which is the matter potential with which the neutrinos are interacting. And you can see that is depending, for example, from the abundance of electron neutrinos minus antineutrinos. So if we send some particles through MSW resonances, and those are either neutrinos or antineutrinos, we are going to modify, which is the abundance of electron, the Y nui, basically the lepton abundance for the electron flavors in the supernova. Or this could be the same if we mix with other flavors. And so this means that as a function of time, we need to take into account that there is a potential that is felt by neutrinos that is changing because the conditions of the star are changing, but also because the lepton asymmetry is actually changing because of flavor mixing. And so here you can see like an extreme example where if we start with this solid line that doesn't include the fact that neutrinos are changing their flavor, and then we end up with this dashed line by taking into account this flavor mixing between the active and the sterile flavors. So this is, of course, inducing large variations in the way we model the production and the amount of sterile neutrinos that we can predict. And then in turn, this would affect also various other quantities that are characteristics of the physics of the supernova. So if we take this into account, then of course we can start to place some constraints on the mass and on the mixing of sterile neutrinos from supernova, and place these constraints together with like a more general framework where we have constraints from other sources. However, again, like most of the supernova bounds that have been considered and that are proposed in the literature are mostly sitting around this, for example, this blue line for the electron neutrinos transforming into sterile ones, and these dotted lines for the non-electron flavors transforming into sterile flavors. But if we take into account that there is this feedback effect and that this has an impact both on the flavor conversion physics of neutrinos as well as on the physics of the star, for example, by changing the lepton fractions and so on, then the excluded regions from supernovae shrink very much. And of course, this study, which we carried out with Anna Suliga, was only taking in consideration like a static hydrodynamical background from a supernova, where on top of it we considered this kind of evolution, but possibly assuming that a full hydro simulation takes into account these effects, and maybe those bounds will also disappear. So we should be just careful when we think about non-standard scenarios in the context of supernovae to model this physics self-consistently. Now, another example on the other extreme are light sterile neutrinos, and those are electron volt mass. And here the experimental landscape is really still giving us very conflicting results. But in this context, then we still expect MSW resonances similar to the ones that we have already seen for Kiwi mass sterile neutrinos. But the difference is that they occur slightly outside, so not really in the protoneutron star, but in the outer regions. And the largest effect in this case occurs during the cooling phase of the supernova, where it could affect basically the electron abundance, and therefore the nucleosynthesis occurring in the outflows that we have in the late phase of the supernova emission. And so here again, when we want to focus on the effects that we expect to have on the electron abundance, then we have to take into account these two beta reactions, which again, where we modify the fluxes of NUI and NUI bar through flavor mixing. And the matter potential that is felt by the neutrinos again needs to evolve consistently, and we will have a direct effect therefore on the electron abundance, which is here defined as the abundance of the electrons over baryons. So in this plot here, you see an example of what we would get for by considering only active flavors that are oscillating or not with these black lines, and the red lines are telling us instead how the YE would be if we actually take into account the flavor conversions. So we did this for the case of an electron capture supernova. And the reason why this is interesting is that we still don't know where the elements heavier than iron are coming from. So of course, with the detection of the kilonova and the gravitational waves from neutron star mergers, we know that a fraction of them has to come from there, but supernovae have for a long time been also candidates for the formation of these elements, and still they are an option. However, in order to initiate their process, we need a YE which is smaller than 0.5. And so in the past, again, light sterile neutrinos were proposed as possible candidates that would then push the YE below 0.5. And this was indeed happening if we forget about the fact that the neutrinos are also oscillating among themselves, and there are all these dynamical effects that need to be taken into account in the modeling. So if we do this, then we end up with a more conservative effect, which is described by this red line, which of course is suggesting that if sterile neutrinos exist, they would have an impact on the synthesis of the heavy elements in supernova supernova, since YE is extremely sensitive to variations due to whatever ingredients could be there. But it doesn't seem that they have an effect such to activate a strong R process, since already in this case, which would have been quite optimistic, we didn't manage to go beyond 0.5. And I think this is basically still the state of the art in the field. So if those are examples that I wanted to just present to connect possible non-standard scenarios that are linked to neutrinos. And of course, through the same arguments, one could think also of other scenarios. But it's possible also to learn about new physics through the diffuse supernova neutrino background. As I mentioned here, in this case, we needed to be careful to think of features that could be eventually detectable modulo all the uncertainties that we have on the signal. And so an example here is the decay of neutrinos, which we can also constrain through the supernova burst, as Gerg also was mentioning. And here you can see that in the absence of decay, we have this blue line. And if a decay of neutrinos occur, then we have an effect on the spectral shape of the signal that we expect. Or also we could consider the mixing between active and sterile flavors for pseudo-Dirac neutrinos, which lead to very characteristic features in the energy spectrum. And Manibrata-san, I think that will cover these topics later on in his talk. So this brings me to my conclusions. Supernovae are driven by weakly interacting particles such as neutrinos. Still, the physics related to neutrinos remains to be understood for what concerns the core of the supernova, but by detecting neutrinos, we have a very strong probe to test the physics of weakly interacting particles, both standard and non-standard. Still, even if we have uncertainties in the modeling of the standard weakly interacting physics in supernova, we already can place bounds on standard scenarios, which would be complementary to the ones coming from other sources. And another observable that we can use in this context is the diffuse supernova neutrino background, whose detection will hopefully occur very soon, that can also give us very clear-cut signatures of scenarios that are non-standard. Thank you.
Thank you very much for the very, very nice talk. And let's see if there is any question or otherwise I have questions. Okay, I'm going to start because in the meanwhile I have a question. So first of all, you said that with the electron neutrinos, like the prompt signal, there is basically no there is no possibility that any weird signal might be attributed to any standard physics in the supernova. Like, for example, no dependence on the equation of states, no dependence on anything.
You mean for the neutronization burst?
For the prompt signal, there is nothing like it's such a clean signal of new physics. If you observe something.
No. So this is only one part of the signal. So I had.
Yeah, no. I mean the burst, yes.
Yeah, so this part here, there have been like a lot of outputs from various hydrodynamical simulations with various masses, various equation of states, and it seems that you can get a difference at most of few percent of this feature. So in a sense, it's like a standard candle. But the question is that what we will actually see at Earth depends on the mass ordering, because the electron flavor is here, but the non-electron flavor is here. So if you swap the two of them completely, you can be unlucky and therefore just miss the neutronization burst. But if we are more lucky, then in principle, we should be able to see like part of this neutronization burst. And then in principle, this could become higher or smaller according to non-standard physics that could eventually still affect the neutronization burst. But yes, it would be a nice feature if we are in the right mass ordering scenario.
I see. Thank you. I have other questions, but like in the meanwhile, let's let other people ask questions. So I think that Thomas was first, and there is Oscar. Please,
thanks. Thank you, Irene, for your talk. Very nice and a grand overview again. You had on one of your slides, you were discussing some bounds derived from coherent scattering processes, or a scenario where coherent scattering plays a role. Could you elaborate a bit on that? I wonder what one can do with that process, because there's only a short phase where nuclei are abundant in the supernova core.
Yeah, so the most stringent bounds, well, those are again projected sensitivity bounds, would come from detectors. So here I didn't show the big picture, but there are many other constraints coming from other probes that are basically already probing these regions. So this would be complementary. The argument here for what happens in the core of the star could be that because of this enhanced neutrino nucleus scattering, one could basically keep the neutrinos trapped into the supernova core for longer time. And so in principle, this could then affect the physics, because if, for example, we assume that we manage to keep them trapped for over 100 seconds, then we could go beyond basically what can be the gravitational collapse will take place before, because the neutrinos have no time to then release energy into the medium. So what we used were very simple arguments of this sort, and just really a back of the envelope estimations, but just by considering, let's assume that they are trapped for a very long time and they are never emitted because they are just interacting with the nucleons. So this is the argument that was used.
Nucleons or nuclei? Because you have written here on the slide neutrino nucleus scattering.
So in this case, well, no, this was mainly nucleons, because it was, of course, it can also take place with nuclei.
Yeah, but there's
it would be the same principle that we have in the detectors, so it wouldn't be a problem for this. Yeah. So it can be considered for any kind of, for both for nucleons and hydron and other nuclei.
Okay, thank you. Thank you.
There is a question by Oscar.
Yes, I have a question related to one of your last slides when you talk about the attempts to explain air process productions in supernova, core collapse supernova, by these electron volt mass sterile neutrinos, because there is a strong needs of an alternative source of the air process from astronomical observations, and the air process appear very early in the galaxy, no? And neutron star merger require a delay times that is related with the time scales of the mergers. So supernova, of course, is the most promising site to explain these early pollutions of the galaxy. By the way, as you have shown in the slides, models predict that YE to have a strong air process. So my question is, there is any other possibility or new physics? Have you any idea of how to reduce the YE and then give rise to a more strong air process productions in supernova explosions?
Yes. So the reason, so the sterile neutrinos were traditionally proposed in these very early papers exactly because they would lead to this very strong change in YE if we consider very simplified kind of modeling of the flavor mixing. So in this specific case, these are the most self-consistent estimations. So assumption is that there is really no hope through sterile neutrinos to make the environment neutron rich. However, there is the possibility that, like in this case, we are only considering simulations that do not include MHD effects. So if one were to take into account, for example, MHD plus sophisticated neutrino transport simulation, this will surely lead to changes into the YE. And so this can determine, even just by considering standard scenarios, maybe it would go in the right direction. Other possibilities could involve, for example, maybe other kinds of non-standard interactions, but I would say that the case of sterile neutrinos is kind of the most extreme one, because we are really depleting the electron flavors, while through other kind of non-standard interactions, we would just diminish the amount of electron flavors. So yes, I think that standard solutions would be actually more promising in this respect.
So just to add to this, I'm definitely not expert on this, but I think that there was a paper by Volodymyr Stagisov, Alex Kusenko, and I think there was George Fuller was one of the authors on PBH neutron star mergers enhancing R processes. But
but I think Oscar was just asking specifically about
Supernova. Yes, indeed.
Yes.
Indeed. Because there is this need to have a very soon pollution of the galaxy. If you look to the extremely metal poor stars, they immediately show a strong enhancement of europium over iron, for instance. And it appears that the neutron star merger require more times to enter into the
may I add to this discussion? I tried to raise my hand. And,
I know. Please.
Yeah, I mean, this discussion is going on, but supernovae as a source of this early R process are connected to one basic problem. There is no supernova explosion which we know which doesn't also produce iron. So if this R process, which is seen in the very early stars, were coming from supernovae, you would already see the R process enhancement at a metallicity of about -3 or -2 solar, which is actually not the case. So there must be a source which is producing R process elements without iron. And you were mentioning, Irene was mentioning MHD. This is quite correct. That is one of the suggestions, but this MHD scenario would be connected to extremely rare stellar core collapse events which produce jets due to magnetohydrodynamical phenomena. Again, this would raise the problem, why don't we see iron connected to that production? In this whole discussion, one should not forget that neutron star mergers, even though they are discussed already as the probably most frequent source, we still don't know exactly how their rate evolution is in the history of the universe, because it's a binary evolution problem, which requires a lot of assumptions in the modeling. And there are scenarios and predictions that neutron star mergers might even occur very quickly after a stellar formation. That means on the timescale of the lifetime of massive stars. That means even within several 10 million years in the early universe, one might already have a significant output of our process producing neutron star mergers. So in summary, what I want to say is neutron star mergers are not excluded as the single only source of our process elements, even the first enrichment. And what the discussion currently may also include is a potential very rare kind of supernovae. But unexplained so far is the question how these supernovae should produce our process elements without an associated output in iron.
Mm-hmm. I see.
Thank you. There is still one question that Manibrata had since long ago. So please, Manibrata.
Okay, I'll be quick. So Irene, I just thank you for the very nice talk. I have a quick question about the KeV cooling, sterile neutrino cooling bounds that you showed. So these calculations, I believe they also depend on the temperature and the chemical potential and the matter profile densities also, right? So which are different at different time snapshots. So how sensitive are your results to these the variations of these temperature profiles and so on for different time snapshots? I mean, would these results change?
We considered a few time snapshots, and as I said, we then considered all these feedback effects by assuming that the hydro background was static, and then considered dynamically all these effects, and the trend was the same. So of course there is sensitivity to time. So for this I was saying, if we had to run a full hydro simulation by taking this into account, then this final bound should be recomputed properly. So it changes with time, but roughly you always have the same effect that those bounds here are really overestimating the extruded region.
I see. Okay, thank you.
But in the papers you can find the different times.
Okay.
Thanks for the question, Mani brother. So I think that there are no further questions, so we can move on. Thanks again, Irene, for the nice talk. And next speaker is